Hello and welcome to lesson number 4 of our trigonometry unit. In this task, we're going to be extending our work with our Ferris wheel, and we're going to be basically looking to graph the height of a rider on the Ferris wheel at a time t. And we'll be able to kind of see that graph as we are looking at it below. So the important facts about our Ferris wheel that we've used before is that the radius is 25 feet. The center of the Ferris wheel is 30 feet above the ground. The wheel makes one complete revolution counterclockwise every 20 seconds. All three of those pieces of information will be important when we're going to try to graph this and also sketch our, figure out our equation too. So we're going to keep all that information in mind, and we're going to be looking to graph it on this XY axis right here. So along the bottom, we have time in seconds. Let me put it up a little bit more. And we have on the left side, we have this as height off the ground. So we want to maybe make a table here to make our process a little bit easier. And we're going to be looking for some specific points and kind of using the information we know about our Ferris wheel we looked at in these 3 bullet points from earlier to fill out that table. So let's do that now. So to start off with, we need a table that is t time versus h of t for height. So we got that right there. So now if we think about our information, we know that we had 25-foot radius equals r, 30 feet for the center, and our rotations are one counterclockwise every 20 seconds. So if we wanted to figure out like how many degrees per second, we would do our full 360 degrees divided by 20 seconds, and we have 18 degrees per second. This is all consistent with what we've worked on in our Ferris wheel work so far this chapter. So we're going to try to get some easy points first that we may not need a calculator for, and then we're going to try to see, well, how can we get some of those in-between points from before. So now if I have time t right there, so I know that 0 seconds in, well, I haven't gone anywhere yet, but I'm basically, remember that I'm kind of on the right-hand side of my Ferris wheel, so I'm right in the middle of it, so I would be 30 feet off the ground. Now, if I am going to start going through the Ferris wheel, if I'm starting on kind of the right-hand side, so like maybe I should draw a little picture down here. So I have my Ferris wheel with our radius lengths. So that point right there, and we're going to be going this direction, is how this Ferris wheel is going to work, if you forget. So we know we have 0, 30. We haven't gone any seconds in, and we're 30 feet above in the air, so I have my red point right there. Next, we're going to skip a point, and we're going to get the next one over. The next easier point, well, how many seconds would it take us to get to the very top? So if we are going one complete revolution counterclockwise every 20 seconds, what I mentioned earlier, well, a quarter turn of that would be 5 seconds later. So 5 seconds in, we are at the very top of the Ferris wheel. So we're adding a radius of 25 to 30. So that means we have 55 as our next point. So 5, 55 would be right up there. Then we can skip again. Another quarter turn would be another 5 seconds, and then we're back down to 30 feet off the ground. So 10 seconds in, we are back down to 30 feet. So now we're on kind of the left-hand side. We're on the left-hand side of our Ferris wheel now, 30 feet off the ground. Keep going another quarter turn. So now we have 15 by, so now back up to down to 5, because we're kind of at the very bottom of the Ferris wheel now after 3/4 of a turn. So 15 seconds in, we are down at 5. And now after 20 whole seconds, our ride is over. So now back to where we started, which was 30 feet off the ground. Like so. So now we could kind of connect these with a smooth curve, and that's what I'm going to kind of do right now. So you can see it right there, and that is basically a sine curve right there. And we know that the equation we've come up with earlier in this unit was that we were using, where can I write this? So let's write at the bottom here. We're using y equals 30 plus 25 sine of 18 degrees times the number of seconds. Because remember that like sine of our angle is going to give us a certain amount kind of on our circle going up or down from the middle. Well, we know that that amount of sine is going to multiply by 25 since that's our radius. And whatever that is, be 30 plus if it's positive and above the x-axis, or 30 minus something when we're below. So now that we've drawn this graph, this is basically one cycle of our Ferris wheel. And so we have kind of finished the first question. So let's see what the other questions are asking us. So in number 2, it asks us write the equation of the graph you sketched. We just did that. So now if we are looking at 3, it wants us to generalize it. And we want to kind of look a little closer at the problem as we kind of are going through this. So we know the equation already. We wrote it was 30 plus 25 sine of 18t. So number 3 says, of course, Ferris wheels do not all have the same radius, center, height, or time of rotation. Describe a different Ferris wheel by changing some of the facts listed above. For example, you can change the radius of the wheel, the height of the center, or the amount of time it takes to complete one revolution. You can even change the direction of rotation from counterclockwise to clockwise. If you want, you can change more than one fact to make sure your description seems reasonable for the motion of a Ferris wheel. So how we're going to change it is that we're going to make our Ferris wheel closer to the ground, so 20 feet above the ground. So the center is 20 feet above the ground. And our radius of our Ferris wheel is, let's say, 12 feet. Maybe not 12 feet. So let's say that it would be 9 feet. Radius is 9 feet. And so we have a smaller radius and smaller Ferris wheel in general. So we'll say that the Ferris wheel takes only half or 10 seconds, we'll say. 10 seconds for one rotation. So if we try to plot those points using that information, let's do that on our graph down here. So we know that the center is at 20 feet above the ground. So 0 seconds in, we are at 20. So now if it takes 10 seconds for one rotation, well, 360 degrees divided by 10 seconds, well, that would mean that we have 36 degrees in 1 second. So if we are going to want to try to graph this, so we know that we have 36 degrees is 1 second. So if we have 10 seconds down here at 10 seconds, that's one rotation. So we're going to be back at where we started after 10 seconds. So now if we think about how this Ferris wheel is going to work, is that, well, we have our starting point where we're going up to the top and then back down to the middle and then to the bottom and then kind of back up again. So we have basically kind of 4 sections where we're going from the right-hand side to the top is 1, top to the left is 2, left to the bottom is 3, bottom to the right is 4. So my 10-second period for this whole thing, after 1 second, we're basically moving through 36 degrees of the circle, but also we're kind of dividing it by 2. So something that might help us to kind of visualize what's going on is we want to try to mark what the maximum and minimum of our graph is going to be. So now what that means is that we're starting out at 20 feet off the ground, and we're going up 9 and down 9. So up 9 from 20 would be up to 29, and then down to 19. So halfway through our ride, we are on kind of the left-hand side. We've gone halfway through the circle. So after 5 seconds, we would know that we're halfway through the ride. If you do 5 times 36, well, that equals 180 degrees. And we could write that over here. 5 times 36 degrees is 180 degrees. 5 seconds in, we'd be halfway through the circle. So we could kind of find the halfway points between 5 and 0 seconds. That's 2.5 seconds. That would be where we'd be up at the top. And now at the bottom, we'd be about 7.5 seconds. So you can see that our height is that we're kind of going up to the top, back to the middle, down to the bottom, like so. And you can see how different that graph is. So if we want to know what the equation is, well, we know we're going to use our sine function because we'll still be doing the same thing. So if I wanted to graph this, well, I know that my middle of my Ferris wheel is 20 feet off the ground. So it's got to be 20 plus or minus something. So we're going to add our radius, which was 9, times our sine. And we know that it's going to be 36 degrees of the circle times the number of seconds that we're going for. And so we basically can say that every 36 degrees, we're kind of moving through our circle. And every 10 seconds, we are finishing one cycle. And so we've got an equation for this. So if we compare the first graph, so we have that kind of taller and spread out more, and we had our equation right there, 30, 25, 18. So now with this one, our 20 was smaller and our 9 was smaller, but the 36 is bigger. So that made it so we have kind of smaller vertically, and then we moved it down to 20, but that 36 is double what the 18 is. So we went all the way out here. So when we doubled that 18 to 36, we're finishing that cycle faster. And we know that by the speed of the Ferris wheel from what we talked about earlier. So we have that, and then we could also even draw in a little line for the middle of our graph. And so that would kind of show where the middle of our Ferris wheel would be. So let's move to number 5. Number 5 is just the equation. So our equation was, for number 5, 20 plus 9 sine 36t. We found 36, remember, from doing 360 degrees divided by our 10-second period for our ride. And that means we had 36 degrees per second. That's how frequently we are kind of going through everything. And so that would be the 36, and the 20 was where the midline was. 9 was how far up and down from that we were going. So now let's generalize this a little bit, because we are now looking at number 6. So in number 6, we are considering the height of a rider on a Ferris wheel with a radius of 25 feet and a center. So now, how would our graph change if the radius of the wheel was larger or smaller? So if our radius was larger, the graph would have higher maximums and lower minimums. And then the opposite would happen if it was smaller. It would have shorter maximums. So like if it was smaller, the max and minimum points would be closer to the middle. So now, what about the height of the center of the wheel was greater or smaller? So that would move our graph as a whole up or down. We changed our equation earlier by making that center of the Ferris wheel a smaller number, so that moved the entire graph of our situation down. So now the wheel rotates faster or slower. So if the wheel is rotating faster, one cycle of our graph would be kind of smaller. And if it was slower, one cycle would be stretched out, is how you might describe that. Now 7 is kind of the sum of the same things that we've been talking about. So 7, how does the equation of the rider's height change if the radius of the wheel is larger or smaller? So we've kind of talked about that already. So if we think about the radius, and so let's say that that is our B value, height is our A value, and the wheel rotates faster or slower. So that's like C. So our equation is basically going to be our A plus B times the sine of our 360-degree circle divided by what C is, and then times our input of time or whatever letter you wanted to use instead of T. And now lastly, we're looking at two different situations where we're trying to get an equation for them. So 8A, the radius of the wheel is 30 feet, the center is 45, and the angular speed of the wheel is 15 degrees per second counterclockwise. So now, if we are thinking about what we were given before we were told how many degrees are in the whole circle. Now it's just 15 degrees per second. And so that means that we just can use that 15. So we would make an equation for this one that would equal 45 feet plus 30 sine of 15 degrees every 1 second. So now if we are doing the radius of the wheel is 50 feet, the center of the wheel is at ground level. You spend half your time below ground is what that would mean. And the wheel makes 1 revolution clockwise every 15 seconds. So this is interesting when it says clockwise, because we're moving in the exact opposite direction. So now if we use some of the other information, radius of the wheel is 50, and the center of the wheel is ground level. So what that would mean is it'd be 0 plus 50 feet of the radius, sine. So now since we're going clockwise every 15 seconds, well, that would mean we'd be kind of going in negative degrees. And so we wouldn't be able to do the original thing we needed to do. So instead of going plus here, we're actually going to make this plus sign a minus. So y is now going to equal to 0 minus 50 sine, and then we're going to do 360 degrees divided by 15t. And that's another sine function that we're going to be looking at. To wrap up this video, I want to take a quick peek at one of our graphs that we started with. So we're looking at this graph. So remember that when you're drawing sine, these, as we mentioned, angles can keep going up and up, or time can keep advancing forwards forever. There's no ending point. That's why I have an arrow right there. So just keep in mind that I could extend this whole function and go a whole nother cycle through it. So I could mark basically 20 seconds ahead for all of these points. So like for instance, this point 15 seconds would now be over here at 35 seconds. And then this top point at 5 seconds would be up here at 25 seconds. And then we would still be kind of starting our second cycle at 20. And so we have our graph here. Like so. And that concludes lesson number 4, entitled More Ferris Wheels. Thank you for watching.